Let's do an electrophoresis example. So we're given particles of a certain size, and they're put into a solution of electrolyte with a certain concentration. We're given the temperature. We're given that we put in 2 electrodes and we hook them up to a voltage source that's 10 volts potential difference, and that the 2 electrodes are 1 centimeter apart. The question is, and we're also given the zeta potential of our particles. So our particles have a zeta potential of 10 millivolts. So given all that, how fast do the particles move through solution? The first thing we have to decide is if we have particles that are small or large compared to the Debye length. And for that, we need to get the Debye length. We weren't given the Debye length for this solution, but we were given the concentration of salt. We know the charges on sodium chlorides, and we're given the temperature, so we can calculate Debye length for this solution. And we've done this solution before, so we know the Debye length is 9.6 10⁻10 meters. We don't know the viscosity of the solution that we're using. We could approximate it, though, just using the viscosity of pure water. We aren't given the field strength, but we are given the voltages that we're using and the distance electrodes are apart. So just using voltage over distance, we can get our field strength of 1,000 volts per meter. So now we're ready to plug everything into the Smolakowski equation. So we've got the dielectric constant of our solvent, the permittivity of free space, our zeta potential of our particles, whatever the E field strength is. For water room temperature, we have a dielectric of 78.5. So permittivity of free space is 8.85 10⁻12 coulombs squared per joule meter. And our zeta potential was 10 millivolts. Our E field strength was 1,000 volts per meter. And we said we were going to approximate the viscosity of our solution with the viscosity of pure water at this temperature. As an exercise, you should go through and verify that this ends up as units of meters per second. And when we get this, we notice that all the numbers here are positive, so we end up with a positive number, a positive 7.8 times 10 to the negative 6 meters per second. Or we could say 7.8 micrometers per second. And so if we have an ultramicroscope and we're watching these particles move across the field of view might be tens of micrometers, and so we can see it takes several seconds to go across, and so we can time the particles and verify their speed. Often this is used as a way of measuring zeta potential by measuring the speed. Note that the number is positive, which means that if we have a positive electrode and a negative electrode, these particles are moving in the same direction as the electric field because they had a positive zeta potential.